Okay, so time to get started. Here's a new topic for today, a new chapter. We're going to finally get into a little bit of calculus. Here it is. We got the first midterm exam coming up momentarily, and we're just finally getting around to doing calculus in a course called MultiVariable Calculus. Seems a little weird. Of course, there's a lot of groundwork that has to get laid. We've done a bunch of stuff. We've talked about vectors and operations and things like that in multivariable spaces, and then also we've talked about multivariable functions and how to represent them and stuff like that. Okay, so I very quickly want to go through and remind you all about single variable derivatives. And I know you know single variable derivatives, right? But there's a certain perspective that I want to take on single variable derivatives. It's a little different than the perspective that you've probably seen in single variable calculus classes. I'm going to do this kind of thing a fair amount in this course, where I'm going to take a topic that you already understand, and I'm going to say, even though you already understand this, let's take a certain point of view on it. And the reason for that certain point of view is because that's the certain point of view that's going to extend most naturally in a multivariable setting, right? So this is kind of depending on how you look at it, first of those. Okay, so single variable derivatives. Y'all remember? Okay, I'm not going to write down the definition. Y'all remember the definition. Y'all remember interpretations about slope of a tangent line and the velocity of the car as it's driving along the road, that kind of thing. Here are a couple of relevant points of view. You all remember linear approximations as one of the applications, and a rewrite of this linear approximations formula. If you look at that difference as delta f, then you can say this, that when you're looking at a single variable function, the derivative is the thing that you multiply by a change in the input to get your linear approximation of the change in the output, right? So the takeaway I want to have on this formula right here is that the derivative is a relationship between an input change and an output change. Now it's just an approximation, of course, because these are finite changes. I mean, the function's curving and stuff, so everything's off a little bit, right? But it's a relationship between input change and output change. Okay. Now, here's another thing that you all remember from single variable calculus. This is the chain rule, right? So the chain rule, and let me go ahead. We can go ahead and splurge a little bit and zoom in. We've got the space. You think of this as, well, that times that is this. This is a tool. If you know how to compute these things, but you want to compute the derivative of the composition, then this tells you how to do it. Okay, but I want to interpret this again a little bit differently. Let's look at this derivative right here. We've got some function f whose input variable is x. And what this says is the rate of change of the input variable and the rate of change of the output variable are related by the derivative of that function. Right. So in both cases, look at both of these formulas, it's a neat fact. In both cases, even though we've thought of these formulas as being pretty different in single variable calculus classes, in both cases the derivative is a relationship between what I'm loosely going to call input changes and output changes. Right? And this is the point of view that I want to take going forward. This is how I want you all to think about derivatives. It's a relationship between input changes and output changes. Sure, sometimes the changes we're talking about are, discrete, finite changes, increments, right? Sometimes they are instantaneous rates of change, but in both cases they're change. So whether they're discrete, displacement changes or velocity changes, we've got input changes relating to output changes, and that's what the derivative is. So this is I've got this written down here. So change in the input relates to change in the output. Now, specifically, notice that it's not just a relationship. The derivative is the thing that you multiply by input changes to get output changes. We are going to eventually recover. Like I say, there's a bunch of different kinds of derivatives we're going to talk about in this class, but our eventual sort of final point of view on derivatives will have this feature, that the derivative is something that you multiply by input changes to get output changes. For the moment, let's broaden it a little bit. For the moment, even though this is a multiplication, let's have the takeaway on this derivative be that it's a connection between input changes and output changes. It's a relationship between input changes and output changes. Okay, so here's some pictures. Again, this is all old hat, but the derivative is a relationship between an input change, so a discrete change, a displacement on the x-axis, and then the corresponding linear estimate of the displacement on the output, on the y-axis. If we're looking at a graph, of course, we're single variable calculus. Everybody uses graphs. And then, likewise, if you have a velocity on the x-axis and you want to know the corresponding velocity of the output on the y-axis, right? So the derivative is a relationship between those velocities. All right, a couple of examples I'm going to let you all read. These are straight out of single variable calculus. I'm not going to spend time on them, but do make sure to read them, make sure you're comfortable, make sure you remember all of that single variable derivative stuff. What I want to do here before we go on to the next section is redraw these pictures. And with the following point of view. These pictures, again, very familiar. This is how you'll see them. This is how you'll see them in a single variable calculus class. That picture right there is a graph. And common and convenient though it is in single variable, that's not something we can hang our hat on in multivariable. So I want to redraw this picture without the crutch of it being a graph. And likewise, I want to redraw this picture without it being a graph as well. Come on, button. Here we go. Okay, so the big takeaway, we have an x-axis that is our domain, on which we're talking about a displacement. And then we have a y-axis that, well, really that's just representing our target, on which we have the corresponding output displacement. And notice I can draw that same picture here. And that's not a graph. On my input axis, my domain, there's a displacement, a change in the input, and then correspondingly on my output axis, again, not on the same axis system. Why would you do that? That's weird. That's graphs, right? There's no need for that. There's an output axis. It's the target, and there is a corresponding linear estimate of our output change. No graph necessary. And then likewise, down here, by the way, you notice just if only cosmetically the sort of the similarity of these pictures, arrow, right? And, arrow. It's just how we label them. One of them we're labeling as displacements. One of them we're labeling as velocities. So likewise, these velocities drawn on a graph setting, they don't have to be drawn on a graph setting. I can separate out the domain, the velocity in the domain, the target, the corresponding output velocity in the target. This is all I need. I don't need to make it a graph. Okay, so these are the kinds of pictures we're going to draw going forward when we're talking about relationships between input changes and output changes. Most of the time I'm going to draw the domain way over here, and I'm going to draw the target way over here, completely disconnected from each other. Input changes, output changes, that's what's going to be sort of preserved. Okay, so let's see that in a multivariable context. It's going to take us a while to work up to that. We're going to start with something that's awfully convenient. This is a great tool for doing what we were just talking about, thinking about a derivative as a relationship between input changes and output changes. I'm going to start off with, again, something that's just very convenient. And that is a parametric curve. If you want to talk about a derivative of a parametric curve, let's, for the record, note that this kind of function is not, traditionally what you see in a single variable calculus class as a single variable function, because there are in-output dimensions, right? You've got position as a function of a single input variable, time. Okay, so what should a derivative mean in this context, and how do I visualize it? For lack of better ideas, and by the way, this is going to turn out to be just exactly what we needed. I'm going to recycle the single variable calculus definition of a derivative. Fingers crossed, I hope this works. We know in some cases you can't recycle this definition. In some cases, if you were dividing by a vector, we know that would be a catastrophic crash and burn. Doesn't work, doesn't make any sense because you can't divide by vectors. But here, H is something that participates as an input. The input, the domain here is R1. H is just a scalar. It's just a number. You can divide by that just fine. And we are perfectly welcome to write down this formula right here. Now, what we don't know, does the product rule still work? And all those shortcuts, quotient rule, chain rule, does that still work? Geometrically, what does this mean? It's not the slope of a tangent line anymore, that's for sure. Slope of a tangent line that's calculus of graphs. We're not looking at a graph. We're looking at a parametric curve. So forget about slope of a tangent line. So we need to figure out algebraically how does this definition behave, and geometrically what does it mean? What does it look like? Is this geometrically natural? Is it physically natural? Things like that. Okay. All right, and so it turns out there's good news answers to all of these questions. The first observation I'm going to make is just about how it gets computed. Here's our definition of a derivative of a parametric curve we just wrote down. Let's break this process down one little step at a time. Here we are subtracting two vectors. Good news, vector subtraction is done component-wise. Just subtract the corresponding components. Okay. Next calculation. I've got to take this vector and divide by a scalar. Right? How do you multiply or divide a vector by a scalar? Answer, component-wise. Right? So that simplifies to that. Dividing the vector by h effectively means you're dividing each individual coordinate by h. How do you take a limit of a vector-valued function? Well, this is something we talked about briefly, though it was, back in the section on limits, and limits are computed component-wise. All right, so the beautiful thing about this definition right here, that definition has several steps in the process. There's a subtraction and a division and a limit, and all three of those steps are performed one component at a time. The first component is unaware of the existence of the other components in that calculation. And so look at what you get. This derivative of a parametric curve has a bunch of components, all of which are straight up good old-fashioned single variable calculus derivatives. Look at that. All right, this is just straight out of a Calc 1 book derivative of this single variable function, scalar valued function R1. That's just the first coordinate function of the parametric curve. Now the parametric curve has lots of coordinates. It's a vector valued function, right? But its first coordinate function has just a single value. So this is Math 111L right here. So that's fantastic news. This Math 111L derivative, we have a bazillion rules for how to help us compute those things. So we do not have to reinvent the wheel and come up with like a new quotient rule and a new product rule and a new chain rule and all that stuff. No, it all comes along for the ride. If you want to take a derivative of a parametric curve, cool. Just do it one component at a time. Everything's fine. It's great news. Okay. How are we doing? Is everybody on board? Okay, yeah, but what does it mean? We've shown that this definition is easily computed. Does that mean that it's useful? No. Right, so what does this mean geometrically? Does this have a physical naturality about it? And it turns out that yes, it does, as it happens. So let's look at, I'm on the, right. Let's look at this picture right here. So here's our parametric curve floating around in space, right, off it goes. Parametric curve. And here's the objects in play in that definition. Here's R of t. And here's R of t plus h. R of t and R of t plus h are just 2 points on that parametric curve. Right. Now let's talk about the difference. That numerator in our limit expression. I didn't write down the limit yet. R of t plus h minus R of t. That numerator is, well, it's this difference vector. It's the displacement between those 2 points, sort of a starting point and an ending point, if you will. Okay, now, what happens as h approaches 0? Well, as h approaches 0, t plus h gets really close to t. These 2 points get closer and closer to each other. That numerator approaches 0. That's not that interesting. Okay. Now I'm just going to make an appeal, and I don't want to get it too into the weeds on this, but let's think about what happens when you divide by h. What happens when you take that velocity, when you take that displacement vector, that purple circled displacement numerator, and divide by h? Well, remember, our premise is h is getting smaller, so as h gets smaller, that purple vector is getting smaller and smaller, sure, but then we're dividing by h, which itself is also getting smaller and smaller. Right? So in the limit, you would expect that it would not be getting smaller. Now, this is where I don't want to get into the and it depends on conditions on the parametric curve and regularity and stuff like this. That's not, we don't need to get into. But you would expect that as it is a ratio of two things that are getting smaller, one would expect the same kind of order of magnitude rate. You would expect that this fraction would not be. Okay, and then so what direction is this thing pointing? Well, these vectors here, these what we call secant vectors between 2 points on the curve, they're not exactly tangent to the curve, but as h gets smaller and smaller, we're looking at points that are closer and closer, and as it gets even closer along the parametric curve, in the limit, you would expect that it would be, in fact, a tangent vector. And again, don't want to get into the weeds, but I think this is a plausible expectation. How are we doing? Everybody on board? Everybody believe it? Okay. All right. So in the limit, if you look at the limit of that expression as h approaches 0, what you get is a tangent vector to the parametric curve. And now, so let's think about that tangent vector. What can I say about the magnitude of that tangent vector? Well, we're looking at, magnitude here. Where did I write this down? Here we go. The magnitude of that displacement vector, which is distance. And then we look at the absolute value of the denominator, absolute value of h. Well, what is h? H is the amount of time between t plus h and t. So we're looking at distance divided by time, and that's speed. This is what's known as instantaneous speed. The limit of distance over time is instantaneous speed. Okay, so our vector here, this derivative vector, it's a tangent vector to the curve, so it's pointing in the direction that the curve is going. Its magnitude is equal to the speed that it's going in that direction. And now I rewind us back to day 1 of this course. A vector that points in the direction you're going and whose magnitude is equal to the speed, that's the definition of the velocity vector. Right? So this is the really nice punchline that the derivative this derivative thing, stylus, that derivative thing, not only is it easy to compute, but it has a fantastic physically natural interpretation. It is the velocity vector of that parametric curve. That makes derivatives of parametric curves really useful. Everybody okay? Everybody happy? Said differently, if you want to compute a velocity of something that's parameterized, there's a handy-dandy formula for how to do it. Just take the derivatives of the components of that parameterization. Okay. All right. So, quick example. Suppose you have a bird flying in the air, and let's suppose its position as a function of time is given by this. Notice that is a parametric curve. This is position in space, right? 1, 2, 3 coordinates. Position in space as functions of t. Okay. By the way, this parametric curve, you may recall this parametric curve. This is a helix, right? Sort of a spiraling up helix. And in fact, birds kind of do this sometimes. They catch an updraft and they just spread their wings out and do like that, and the updraft and they kind of tend to go around in circles so they don't get out of the updraft. So this is kind of physically natural, right? Anyway, I think it's fun. So what's the bird's velocity as a function of time? Well, velocity is the derivative of the parametric curve. Just established that. We compute derivatives component-wise. We just talked about that a few minutes before. And these single variable derivatives here are old news, ancient history. Derivative of cosine is negative sine, etc. Right? Derivative of sine is cosine. Hope y'all remember all of these. By the way, a quick reminder, prerequisite for this course is Calc 2. Prerequisite for Calc 2 is Calc 1. So we will assume that you are not only knowledgeable about single variable derivatives, but that you're proficient, that you're good at it, that you can crank out derivatives quickly and reliably and accurately, right? So it's a skill, right? It's a bunch of little techniques and facts and algorithms that you have to be good at. So make sure you are thoroughly practiced and proficient with doing that kind of thing. And there you go. Okay. Y'all will also remember from calculus, single variable calculus classes, questions that look like this, where you have an initial position and a velocity vector given to you, and the question says, hey, reverse engineer, figure out what is actually the position function. Right? So let's find position as a function of time. We know if we had position, the derivative would give us the velocity. Here we have the velocity. How are we going to find the position? Hopefully no surprise. The answer is antiderivative. Right? Velocity is the derivative of position, so position is the antiderivative of velocity. Y'all willing to believe that one? Pretty believable, I think. So, okay, fine. We were given the velocity. We take the antiderivative of both sides. And how do you take an antiderivative of a vector? Well, now here's another thing I'm going to pose as highly believable. Derivatives are computed component-wise. So, antiderivatives also computed component-wise. So I can just look at each component individually and compute their antiderivatives individually. Okay. All right, and so again, a bunch of single variable calculus, and again, make sure that you're good at this. These kinds of things, yeah, these were easy ones, right? But again, Calc 2 is a prerequisite for this course. In fact, it's an enforced prerequisite for this course, right? So that's because it is very significant. All this Calc 2 business, substitutions, integration by parts, I think trig substitutions are really important. This kind of thing. Trig integrals, various kinds of trig integrals. You'd be surprised how often this stuff comes up. So make sure you're good at those kinds of things too. All right, now we were asked to find position as a function of time. We are close to done. We have most of what we're interested in here. What we don't have is what these constants are. So we need to work out those constants at this point. Now, here's another common mistake that students make. Very common. It's wildly inaccurate. A lot of students think that, these constants are always just the initial values. Well, that's just not true. For example, check this out. Right? Let's just plug into this formula. Let's plug in t equals 0. Plugging in t equals 0, well, my initial position is given as 325. That's the 325. That's, again, some students are expecting to be C1, C2, C3. But notice it's not. 325 is not C1, C2, C3. There's other junk in the equation. Why is there other junk in the equation? Well, there's the little matter of this antiderivative function there. Right? That's the antiderivative function that we found here. This stuff does not have to be 0. It just doesn't. Right? Now, so a lot of y'all may be thinking, but man, I did so many of these back in Calc 1 classes, and they always were. Right? And as a result of those functions having always been 0, it just always was the case that these were the initial values. So why, if this isn't always true, how does it keep happening over and over again? Well, there's a really simple answer to that question as well, and that is in a lot of high school calculus classes, the only functions that they give you to deal with are not trig functions. In a lot of calculus classes, they overwhelmingly give you polynomials. And here's the thing, an antiderivative of a polynomial, right, will be, of course, another polynomial, but it'll never have a term without a t in it. Antiderivatives of constants have a factor of t. Antiderivatives of t has a factor of t. Antiderivative of any power of t has a factor of t. And so it's usually, something like this, c1t plus c2t squared and plus ... And no surprise, when you plug in t equals 0, plug that into there, and this ends up being 0. So the illusion that initial conditions have to be integration constant, that very false illusion is just a consequence of what I'm going to call kind of laziness of examples, a choice of examples in some other calculus classes. So anyway, be really careful with this. So for one thing, assuming that this is your integration constants will give you wrong answers sometimes. That's not even the biggest point. The biggest point is, assuming that these will be your integration constants is logically nonsense. That's the big point, right? Something that is logically nonsensical, but even if it, in this particular case, if it had given you correct, like look in this case here, if you look at that, we got 2 out of 3, right? We would have gotten the correct answer here for 2 out of the 3 constants, and the wrong answer on only one of them. Would you get partial credit? Nope, because your argument's nonsense. If you just cite these numbers as your integration constants, the argument is nonsense. And it's a pure coincidence that numerically some of them have to be right. But remember, this is a class about ideas. It's not a class about answers. Right? So be really careful with this point. Make sure to go through the process, plug in t equals 0, solve as necessary for what those constants are. I got to see that process. Okay. Moving along. More derivatives. Not a parametric curve. This is this is going to feel like a more general discussion. It's for any multivariable function, what should a derivative mean? Now, here's where, if we were to try to write down the old definition, limit of f of x plus h. Oh, wait a second. Well, x is a vector because look, our domain is made up out of vectors. So if x is a vector, well, that means h has got to be a vector. And that means I'm dividing by, well, that same h, which is a vector. This then is a multivariable limit as h goes to 0, and it's complete garbage because you can't divide by vector. So here's where we really can't just rip off from Calc 1. Right? And what are we going to do about this? I'm going to go back to the discussion that we just had about interpreting derivatives. Derivatives should be interpreted as, look, I've got an input change and I want to understand the corresponding output change. It's a relationship between input changes and output changes. And I'm just going to kind of brute force write down such a relationship. So here's the question I would like to consider. Suppose I'm at this point, some point in the domain, let's call it A, whatever. Suppose I'm moving with some velocity in that domain. I don't know, whatever, let's call it V. Don't forget now, by the way, when you're moving around, velocity is the derivative of the position function. We just talked about that. Okay. In this scenario, where in the domain, I'm at the point A and moving with velocity V, what I want to know is, this output point that comes from that input point, I want to know what is its velocity, namely derivative. Right? So given V, I want to know the corresponding output velocity. This is our goal, and how I'm going to brute force make that happen is on the next page here, but this is pretty straightforward, just a matter of doing it. Okay, if I'm at this point A and moving with velocity V, I can actually kind of make that happen with a parametric curve. Here it is, the parametric curve that is at A moving with velocity V. I could just write a parametric line that starts at A and is moving with velocity V, and I know all about parametric lines. There is the formula for that parametric line. Plug in t equals 0, you're there. Compute the derivative, you get that V as desired. Right? So we have constructed a physical scenario where, per this premise, I am at A and moving with velocity V. Okay, so having done that, if you're at A moving with velocity V, there's that input curve. I could plug in and see what the corresponding output curve is. These are maybe, I don't know what the output is doing. The input, x is a function of t. Again, we have that parameterized. Just plug that into the function. That gives you the outputs f of x of t. Everybody good? Now, reminder, what do we want? Given an input velocity, my goal, what I'd like here is to figure out what is the output velocity. I would like to know what is the velocity there. So how are we going to find the velocity? Well, reminder, velocities are derivatives. We're just going to take the derivative with respect to t of that output curve that we just wrote down. Okay, so let's take the derivative with respect to t. That will give me that output velocity, and there you go. That's in fact. Let me highlight this a little bit more cleverly. There we go. Given an input velocity, I have here a formula for how to compute the corresponding output velocity, and it's just very brute force. It's very just to kind of lay it down. This is kind of what it has to be. Yeah. Okay. And that's the formula that I have up here. It's the derivative of f of that parametric curve, a plus tv. Straight out of this picture. Okay, one little quibble, minor point. What I have written here, this thing here is a function of t, and that's Not, in fact, quite what I want. What I'm really, in fact, interested in is, look, presumably I am at this point moving with velocity v. It is specifically when I'm at that point that I want to know the corresponding output velocity. So now how are we going to isolate that specific moment? Well, when are we at this point? Right? We've got a parametric curve here that goes all the way along that whole line. At what value of t am I actually there at the point A? I want just to be at the point A, and the answer is that it's where t is equal to 0. Right? So this derivative expression, this derivative gives me lots of different velocities. It gives me, let's see here, let me make the picture. It gives me, for some value of t, it gives me that velocity, but then a little bit later it gives me that velocity, a little bit later it gives me that velocity, and then eventually it gives me that velocity. Which one of these red vectors do I want? Oh, well, I want that one. I want the velocity when my output is at f of a. Therefore, when my input is at a, and therefore when t is equal to 0. So it is at the moment when t is equal to 0 that I'm interested in that formula. Everybody happy? And that's why I have this little thing here. Let me zoom in. This little thing here. That vertical bar is just a way of saying, look, do this derivative at that specific value, t is equal to 0. So again, that is just to isolate the specific derivative that I want, the output at specifically the right moment. Okay, so this is our formula. This is what I'm going to call a directional derivative. Directional derivative. Here's the formula for the directional derivative. So that we don't have to write down this great big clunky formula all the time, we have a notation. The notation for directional derivative is this. By the way, FYI, not every notation for directional derivative is the same. Different books make slightly different choices. I think this is going to be recognizable in any context. But you might see it drawn a little bit differently, written a little bit differently in other contexts, and no problem. It's just notation. Okay, so let's talk through the notation. Directional derivative, D for derivative, I guess. I suppose it could be directional. Conveniently, we don't have to decide. Okay, so that says derivative. Now, keep in mind, we can't just write down f prime, right? This derivative is an ambiguous thing in this context. Specifically, we are talking about the derivative not just at a certain point, but the derivative also presumably when I am moving with a given input velocity. So this input velocity, you might say, describing what kind of a derivative I want. Namely, under what circumstances do I want to know the output velocity? This input velocity is one of the sort of premises. It's one of the parts, moving parts that goes into the definition of this directional derivative. So I've got an input for this notation. Not only do I have to tell you at what point do I want to evaluate the derivative of f, but with what velocity in the input am I computing the directional derivative of f? Okay. So the convention that I'm using here, anyway, is the velocity vector is a subscript of the capital D. That's just a convention. Again, you might say that this is telling you what kind of a derivative. We're taking a derivative where the input velocity is v. That's the kind of derivative that I'm taking of f. And then, of course, just like any derivative, the derivative, you have to, if you want to get the actual output value, you've got to tell me at what point are you evaluating that derivative. Okay. Everybody on board? Does anybody have any questions about this construction or any of these conventions, notation? Is everybody good? Okay. All right. So now I have to talk about an awkward point. Oh my gosh. So this is This is weird and annoying, but what I've defined here is not universally accepted as the directional derivative. There are some different conventions that are made in different circumstances. There is a school of thought that says, well, look, let's just I'm probably not going to represent this school of thought 100% fairly because I don't subscribe to it, right? But anyway, it's my class. So as the school of thought goes, well, look, the word directional does have the word direction in it. It doesn't say magnitude derivative. It says directional derivative. And so we shouldn't be using a direction and a magnitude, so the school says. And so the way they deal with this is they say, look, this whole thing here, no fair. You're not just moving in a direction; you're moving in a direction with a magnitude. So we're only going to allow unit vectors, just unit vectors as the velocity, only unit vectors, because after all, semantics. Okay, so. A little bit of sarcasm there. So there is a resulting definition. It looks exactly the same as the definition I just wrote down, but there's the restriction in the premise of what that input velocity can be. That input velocity can only be a unit vector. Now I'm not going to do that because it is a very useful. Semantics aside, it is highly physical and natural to have a situation where I'm moving with a velocity, non-unit velocity in the domain, and needing to therefore, know the related corresponding output velocity in the target. This is very natural, and I just don't think the semantics are worth quibbling over. Right? Now, confession: it is also true that if you restrict your attention just to unit vectors, that fact that this is a unit vector, that gives you more information to work with, and in fact there are some interpretations that can be made if you make the choice that I'm not going to make here. There are some additional interpretations that will allow you to compute some interesting things, and that's nice, right? But I still think it's an unnatural choice. So what I'm doing in this book is I'm going to define directional derivatives the way I've done here. This is for any velocity. That notation means this formula. And then in the next section of this book, I'm going to give a subsequent discussion of what I'm going to call a different thing. I call them unit directional derivatives. And I think that's a pretty reasonable choice of terminology. Unit directional derivative to suggest that the input velocity is a unit vector. So all the benefits of this other point of view on directional derivatives, we're going to get all that. We're going to get all the benefits, right? But we're going to retain what I think is the very natural definition, where this velocity vector can be anything at all. And by the way, I think in higher levels of math, this is what everybody does. And this restriction to unit vectors, I've only seen it in lower math contexts. Okay, anyway. All right, enough said on that. Okay, so what is our directional derivative? This is a rehash of things we've already talked about. Where did we get this formula for directional derivative? The whole point, the definition, in fact, that we made of directional derivative is that if this thing is your input velocity, then this thing is the output velocity. So directional derivatives are output velocities where we assume that v is the input velocity. So it's a relationship between input velocities and output velocities. Just like we our sort of our new launching point perspective on single variable derivatives. Okay. No surprise, I hope, that there is a sort of a displacement analogy. So if v is your input displacement, then the directional derivative is the linear approximation of the output displacement. So totally analogous, just like we saw in single variable context. Okay. All right. So let's talk about different contexts in which this can make sense. We've already talked about this one here, where if you have a function from a multivariable domain into a multivariable target, then it's a relationship between input velocity and output velocity. What happens, I ask, rhetorically, what happens if our output, so our target, what happens if our target is just R1? So instead of a vector valued function, what if we have a scalar valued function, just a real valued function? Does that change anything? And the answer is no, not at all. Not at all. If you have an input velocity, if you are moving through your domain with some velocity, there will still be a velocity in the target. Velocity makes perfectly good sense in a single variable context. In fact, this is something that allows us to make more sort of physically relatable interpretations. Here's one. Let's suppose that this is longitude and latitude, position on the map, right? And then let's suppose that the target over here represents temperature. Again, this is very physically relatable. We've all seen weather maps online, and you could pretty reasonably imagine a scenario where you are at a certain point on the map and you're in your car and you're driving with a certain velocity. Right? We've all done that. Can't you see how it would be pretty plausible that you might want to know what then is the corresponding rate of change of temperature that you're experiencing as you drive down the road? It's perfectly natural. Everybody see what I'm talking about? So, if you know your velocity along the map, you want to know how fast is it getting hotter. Okay, so very related. This could be all sorts of different things. This could be altitude, and you want to know how fast are you increasing altitude? How many feet per second are you climbing as you drive along this road? Again, very plausible thing you want to know. Okay, here's a different scenario. Let's suppose you have a single variable input, single variable domain. Is this still something that makes sense? Yeah, totally. You could have a single variable input, be moving with a certain velocity in your single variable domain, and then correspondingly want to know what your velocity is in your multivariable target. Now, you may look at this picture and think, hey, that looks like a parametric curve, and kind of, isn't this the same as a parametric derivative? And kind of. Yeah, it's really close. There is one little asterisk that we have to talk about. If we think of both of these as, if we think of this, position in this space as being a function of time, there is a little minor consequence of that, and I'm going to draw a t-axis over here. So we're going to think of position there as being a function of time, and then correspondingly, position over here is also a function of time. And the directional derivative is a relationship between these velocities, right? The parametric derivative, though, is not exactly the same thing. The parametric derivative is derivative with respect to time, right? Not this other parameter. This other parameter, let's give it a name. Maybe it's S, right? So the derivative of the parametric curve, the derivative of, so the velocity vector of that parametric curve is the derivative with respect to t, right? The directional derivative is the derivative with respect to s. So, not exactly the same, but if s and t are the same, or more to the point, if ds dt is 1, said differently, if v is equal to 1, if v is equal to 1, then of course these are the same. So when v is equal to 1, the directional derivative is the velocity vector of the parametric curve. Okay, so one little quibbly little detail that has to get mentioned. Okay, let's compute. Let's get our hands dirty. Here is a real valued function on R3. Maybe that represents temperature in this room, right? as a function of position, or maybe it represents, I don't know, there's lots of physical examples you could think of. And I'm going to consider the scenario where I am at a certain point in this domain. I am at this point 1, 2, 0. I am moving with a certain velocity. In this domain, my velocity is 2, 1, 3. And correspondingly then, I would like to know what is the rate of change of the output of the function. Now, the output of the function this is real valued, of course. It's just real valued. So we don't have a multivariable output. We have just a R1 output. Nevertheless, when I'm here moving with that velocity, I want to know what is the corresponding velocity in the output. Okay, so this is very plug and chug, very straightforward. Okay, so we know velocity is the directional derivative. That's the motivation of our definition for directional derivative, is it gives us the rate of change of the output. Right? Any questions? Everybody good? We on board? Here's our definition of directional derivative. That's just a recopy. I didn't really do anything. That's just a recopy. Okay, well, A is given. There it is. So A is that. Let's see here. V is given. So V is that. And therefore, A plus TV, the parametric curve in the domain, is this. Now again, all I did is just kind of crank out a little bit of chapter 1 vector algebra. Just A plus TV, write it down, plug it in. Okay. All right, now we need to plug into our function. Okay, wait a second, what is our function? Here we go. Our function is x squared plus yz. That's the f that we need to plug into. X squared plus yz, coming down here. This is x squared plus yz. Notice x squared plus y z. There it is. So all I did there is plug into that function f, which is x squared plus yz. Everybody happy? Okay. And now I've got a little bit of algebra to do. I'm going to multiply all this out and collect terms, etc. So go ahead and do all that. That simplifies to this. And now that I have all this, this whole thing here, f of a plus tv, I've multiplied out. I've plugged into the function. I've multiplied out the result. Now I see exactly what I'm going to be taking a time derivative of. So this single variable calculus at this point, good old derivative with respect to t, and that gives you this. And recall that, of course, we don't want to know that as a function of t. What we really want is to know what is the value of that derivative at t equals 0, because it is at t equals 0 that we're actually at the point that we're actually interested in. Right? And so you got to plug in t equals 0, and that gives you our answer 10. Everybody okay? Don't forget, I think this is a standard point in Calc 1 classes. You can't plug in t equals 0 first and then take the derivative. That doesn't make any sense, right? You'll always get 0 for one thing, because t is a constant. You'd be taking the derivative of a constant. So anyway, don't step on that little landmine. Occasionally students do that. You have to take the derivative first and then subsequently plug in t equals 0. Yeah. Okay. Alrighty. All right. Now that was a real valued example. So R1, so just a single output value. What if we have a vector valued output? So something more like this, where the output itself is a vector. How does that change things? The answer is not very much. Here's such an example. Here we have a function from R3, see the 3 input variables, to R2. Now we have 2 output variables instead of just 1. Same pattern. Plug and chug. Slowly and carefully. It all works out. Here we go. So now in this question, we want to compute a velocity. Velocities are directional derivatives. We're given that we're starting at the point A and moving with velocity v in the domain. Now, just for convenience, I've made it the same A and the same v, whatever. So here we go. The velocity is the directional derivative. Directional derivatives are this formula. Plug in. Now, again, just like last time, A is that. V is this. So A plus TV is that. Chapter 1, multiply out and collect coordinates. Now we're going to plug into the function. Okay, wait a second. What was our here's our function. The function f is xy times yz. Okay, now keep that in mind. Xy, excuse me, I said it wrong. xy comma yz. Xy comma yz. Okay, here we go. Okay, so x, y. So there's my first coordinate of my output is x, y, and now continuing y, z. All I've done is compute f. Point being that f is x, y, y, z. Hope everybody's on board and happy with that. And okay, well, multiply it out. Again, just algebra. Take the derivative. At the very last second, of course, and no earlier, plug in t equals 0. And there we go, we get 5, 6. So, I mean, it's not that different. I guess one difference is, look, when we plugged into the function, yeah, we did get a vector. That's true. We didn't get a real number. We got a vector. So, no problem. We need to take a derivative of that vector-valued function. Can you do that? Yeah, sure. We have a formula for derivatives of vector-valued functions. Just do it one coordinate at a time. One coordinate at a time, thus giving you that. So, it's not really that different for vector-valued functions. Okay. So there's more examples in here. I'm going to let you all read the more examples. I do want to point out one last thing before we go on to unit directional derivatives, and that is that if you have a vector-valued function like so, these directional derivatives of that vector-valued function, directional derivatives of a vector-valued function can be computed component-wise. Just like parametric curves. So you remember parametric curves, if you want to take a derivative of a parametric curve, you do it one component at a time. We say component-wise. Likewise, directional derivatives. And there's a really easy way to see why it is that directional derivatives can be computed component-wise. And that is that directional derivatives, let's go back to our definition, directional derivatives are derivatives of parametric curves. They are literally derivatives of parametric curves after a certain fashion, right? So they're special parametric curves that we set up a certain way. But all derivatives of parametric curves can be computed component-wise. These are derivatives of parametric curves. Therefore, you can compute component-wise. Yeah, everybody good with that? Okay. So how does that affect us? I just want to point out in recognition that you can compute this component-wise, that if we were to go back to this last example that we just did, and if we were to suppose that we looked just at that first coordinate, let's view this as a real valued function where that's just xy. How would that calculation go for just xy? Well, what's happening in the domain is still the same. blah, blah, blah. We get down to the value of the function, and here's what the value of the function would be. And now, of course, don't forget, there is no second coordinate. We're considering just xy. So there's xy, which still simplifies exactly the same way. Right? And when you take the derivative, that derivative is done component-wise, and so it's the exact same derivative, and you get, when you plug in t equals 0, 5. Right? And so if we had computed the component, if we had computed the directional derivative of the first component by itself, we would have gotten 5. And if we had taken the derivative of the second component by itself, we would have gotten 6. It's the exact same algebra. Right? So anyway, I just wanted to point that out, as that makes this formula here, I think, highly believable. How are we doing? Does anybody have any questions about this? Everybody's happy? Okay, so let's talk about unit directional derivatives. Now again, this is this kind of alternative perspective on directional derivatives. Pros and cons. The obvious disadvantage of considering unit directional derivatives only, in other words, of only allowing your velocity vector to be a unit vector. The obvious disadvantage is now your velocity vector can only be a unit vector. Right? You're restricting the breadth of application. This only applies to a much more restricted set of cases. So that's unfortunate. But there are some advantages, and so in this section I'm going to show you some of those advantages and how you can, in some cases, make use of this idea. So in other words, this is not a 100% silly idea. There are some nice aspects of unit directional derivatives, but they're not. This is certainly not a good only point of view on directional derivatives, in my opinion. Okay, first thing I want to point out is that this formula for directional derivatives that we made in the last section is what I like to call scalar multiplicative. Here's what I mean by scalar multiplicative. If in your velocity vector, let me make that visible, here we go. If in your velocity vector there is a scalar factor of, let's say, k, you can factor out that k, leave only the sort of the leftover that's in that vector, and that works just fine. So you can, another way to say this, you can factor scalars out of the velocity vector. Now, this is not immediately obvious that this is true, but it is algebraically pretty it's an eyebrow raiser, right? That's a neat property to be true if it's true. And let's show why this is true. It's a very straightforward calculation. Let's compute this thing, where again you'll notice we have this scalar factor of k sitting right there. I'm just going to compute it directly. This is a brute force calculation. Brute force calculation. Here is the definition of a directional derivative. Notice my velocity vector that I'm putting in there is, as indicated, kv. Otherwise, this is just straight up definition of directional derivative. Okay. Let's see here. What am I going to do about this? I'm going to make a substitution. You'll notice that what's actually in this resulting algebra, what's actually being multiplied by v, is t times k, which I'm going to rename now as s. I'm just going to rename that s. Okay. And let's see what we got here. We're taking the derivative with respect to t of what is more visibly a function of s. And I remind you of the single variable chain rule. The single variable chain rule says df dt is equal to df ds times ds dt. Single variable chain rule. Right, and let's write that down. So notice what I have here, we're taking now the derivative with respect to s. See the s now there? And then we're multiplying by ds dt. How we doing? Everybody happy? Again, that's just a little single variable chain rule. Now, this is going to simplify actually really nicely. Let's look at ds dt here. What is ds dt? Well, that's an easy one. ds dt is k. When s and t were defined to be very closely related, so that's easy. That's just k. What about the rest of this thing? What is that? That is let's see, it's a derivative of a parametric curve. It's a derivative where we look at the output values where the inputs are following an input parametric curve. Oh my gosh, that's very familiar. We are in fact taking a derivative with respect to that same parameter at the moment where s is equal to 0. This is a directional derivative. This is straight out of the book definition of the directional derivative, where the velocity vector is v. And, some students get a little uncomfortable with this and say, wait a second, I thought the definition of directional derivative was in terms of t. This is in terms of s. And the observation I have there is that in both cases, it's just a dummy variable. Right? That's just a variable that we're using for the purposes of executing the derivative we need. It's not part of the answer. So I could rewrite the definition of directional derivative where instead of using t, I'm using q. Still the same idea. Right? So that is dvf. And I want to take a pause on this for a second as well. How are we doing? Okay. Yeah.
Generally, should we be thinking of t as time?
I think very often that's convenient. Now, in this case, what we're doing specifically right here, interpreting that as that, it's kind of more useful for this, at this particular moment, to think of s as being time, right? But yeah, sometimes, no pun intended, t is best viewed as time. Yeah, that's right. Yeah. It depends on the context. Yeah. Great question. Anybody else? Okay. Alrighty. So there we go. That's what we were trying to prove. So this scalar factor there has factored outside of the directional derivative. Okay. So who cares? What are we going to do with this? Aside from the fact that every so often it's useful to know algebraic properties of something. I'm going to apply that to a very specific scenario. That specific scenario is where I have a velocity vector v, and I want to reinterpret a velocity vector as having a scalar factor hidden inside of it. Velocity vectors, after all, the magnitude is the speed. Right, so let's think of that velocity vector as being speed times, and speed being the magnitude. This thing that's left over is a unit vector. Yeah. Well, now we have a velocity vector with a scalar factor, and we've got this brand new observation that scalar factors factor out of directional derivatives. So let's just write that down. Here's our velocity vector. It's got this scalar factor of speed. Let's factor out that scalar factor of speed. What remains is just the unit vector u. That's pointing in the direction that we're moving. And we have this as our conclusion, right? So here, all I've done in this formula here is I've factored out speed out of a directional derivative. And now I can reinterpret this. So don't forget, just a reminder, speed is the magnitude of the velocity vector. Directional derivatives, as previously discussed in the last section, are the derivative of the output. So this is a neat result. This thing, this unit directional derivative, and I emphasize this, with the unit vector direction being the velocity that we use for that little calculation. That unit directional derivative here is the thing that you multiply by input speed to get output velocity. And that just kind of the way that rolls off the tongue, right? The sort of the beats of that little statement are extremely familiar. That harkens back to, in Calc 1, a derivative is a relationship between input changes and output changes. Here, this unit directional derivative is a relationship between input changes and output changes. How about that? That's a neat feature, right? This is a strong appeal for unit directional derivatives. Okay. Now, I would quibble a little bit and say, yeah, well, this is an output velocity, but this isn't over here. That's a magnitude, right? So this is not a perfect reenactment, sort of, of what we saw in single variable calculus. Nevertheless, it's got some of the earmarks, right? But this is not perfect. Okay. All right. Alrighty. So here's that interpretation. The unit directional derivative. Here's that term, unit directional derivative. That's what you multiply by input speed to get output velocity. That's nice. Likewise, if you're looking at displacements, same kind of thing holds. This unit directional derivative, that's what you multiply by input distance. Now, not a vector, just a distance, just the magnitude of the vector. The magnitude is what factored out, right? So that's what you multiply by input distance to get output displacement. Here's a picture. Suppose our scenario is that we've got an input velocity given to us, and we want to know what is the corresponding output velocity, namely the directional derivative. The unit directional derivative point of view on how to take an input velocity and get an output velocity is to take that input velocity, unitize it, use that unit vector input to get a unit directional derivative, and then having computed your unit directional derivative, then multiply by the speed to recover your actual directional derivative. So now this is me taking a pot shot at unit directional derivatives. It's like if you want to get from here to here, why go the long way? Right? How about just do that? Pros and cons again. I just wanted to point that out. Okay, how are we doing so far? Is everybody happy so far? Okay. All right. Okay. You do now have a choice in terms of how you compute directional derivatives. You could, on the one hand, you could compute that directional derivative straight out. The other alternative, as we just kind of walked through, is if you want to compute a directional derivative, you could compute the unit vector first, use that to compute the unit directional derivative, and then subsequently multiply by the speed to recover the original directional derivative. So take your pick. Which one would you like to do? Now, I am going to show you some examples where one or the other of these is actually easier to do. Sometimes the unit directional derivative is easier to compute. In some cases. And if that's the case, then yeah, by all means, unitize. Give yourself the luxury of computing the sometimes easier unit directional derivative. And then, multiply by the speed. How hard is that? That's not that big a deal. Right? Arguably, there's very little difference in the processes. It's just I divide by a speed and then I multiply by a speed. Right? So, nevertheless, sometimes the unit directional derivative is easier to compute, and in such cases, This is a great idea. Okay. Here's another situation where unit directional derivatives are useful. Sometimes it is, in fact, what you're interested in the first place. Sometimes you don't want to know the actual velocity of the output. Sometimes what you want to know is the unit directional derivative, in which case, compute the unit directional derivative. That's fine. Then there's a variation of that where you can instead say 1 over v times the directional derivative is the unit directional derivative. Sometimes it's the case that what you actually want is this thing. That's what you want, but it may be easier to compute the directional derivative. In which case, it's easy to then subsequently divide by the velocity to get the unit directional derivative you actually want. So don't make the mistake of, I'm always going to do it this way. Or, make a choice between these two and decide this one is the one that I always want. That's not the case. Sometimes you want a directional derivative. Sometimes you want a unit directional derivative. You got to make the appropriate interpretation and make the appropriate choice. And then likewise, sometimes one or the other of these is easier to compute. So the last thing I'll say before we call it a day is just be aware of the relationship between them, and then know which one you want, know which one is easier, and convert if necessary. Okay, all right, we'll call it a day right there. Let's see here. Oh, 2 things real quick. So first of all, don't forget we have an exam on Monday. Hard to believe. Feels like we just started the semester or the term. But anyways, exam on Monday. All the stuff that we did today with derivatives is not fair game for the exam. So I don't really expect you this weekend to be working on derivatives homework questions. Kind of assuming that you're going to be doing exam prep. And I encourage that, right? So with that in mind, all of the exercises that are being assigned for today, those exercises are not actually due until Wednesday. Right? So you still have a 2-day deal. It's just that your 2 days starts as soon as the exam's over on Monday. So anyway, keep that in mind. On the other hand, if you're feeling solid for the exam and you got nothing better to do and you want to get started on these, of course, you're very welcome to do that, but I'm not assuming it. The other thing, quick announcement, is I forgot to bring the homeworks to return. They're in my office. If you would like to have your homework back so that you can have it to study with over the weekend, just come up to my office right now. I'll pass them back, no problem. Anyway, I'm going to head to my office right now.